so let's talk about 12.1 today. 12.1. Some of the stuff you've done before, so it really is review. Other stuff will be a little new. Okay, so today we are talking about polynomial functions. All right, polynomial functions. So a polynomial function is the sum of power functions, meaning it's a variable raised to a power. It has one or more terms, items that are being added or subtracted together. So each little packet is called a term. All of the variables have positive exponents. There are no variables in the denominator. And they are continuous graphs with smooth, rounded terms. In other words, you're not going to have any like sharp peaks where it meets very suddenly and turns. They're all going to be nice and round and smooth. All right, so certain traits of these polynomials. Okay, you know some of them. Okay. Things that are not polynomial functions. So let's stay over here on polynomial functions really quickly. Okay. Things that are polynomials. Anything that has nice rounded corners, right? Like our quadratic is one. You've talked about cubic functions before. Notice how those have really nice rounded curves. Polynomial would be something like x cubed plus 2x squared minus 4. Okay, a polynomial could also just be a number like -5. You could have something in factored form, so y equals 2x plus 6, x minus 2 or something. Okay, so they're going to be all the things that you're pretty familiar with. Things that are not polynomial functions. Okay, things that are not polynomial functions. These would be things that are not continuous. Meaning you can't draw them without picking up your pencil. Another thing would be anything that has sharp turns. Okay, so sharp turns. Negative exponents. Stop and think about it. If it has a negative exponent, that means that you'd have eventually a variable in the denominator. We're also not going to have fractional exponents. Those are different types of functions. Okay, like I said, any variables in the denominator is not a polynomial function. Denominator. And examples of non-polynomial graphs. This right here, we have this sharp point. It's not rounded, like an absolute value. Also, if you had something like this, that the graph had a break in it, that's not a polynomial function. Let's say we had something like 5x to the negative 2 minus 1. Remember, x to the negative 2 is actually going to be 5 over x squared, so that's no bueno. If we had something like, 4 over x plus 2, that's no good. Let's see here. If we had the square root of x minus 6, that would not be good. So just trying to give you a couple of examples. Notice all over here, all of our exponents are positive. All right, so graphs of polynomial functions. When we are graphing polynomial functions, we are going to use interval notation. Interval notation when representing the x values where the graph is increasing or decreasing. stop and think really quickly what it means to be increasing. I think most of you would say gets bigger, right? But what gets bigger? We have two different variables. We have x and we have y. We are concerned where y is getting bigger, okay? And same thing down here where y gets smaller. But I want to draw some attention to the wording here. Notice that this says representing the x values. So we did this a little bit at the beginning of the year, and that's where you guys had the most trouble. Your answers to increasing and decreasing will always be the x interval. So the question that I'm asking when I say increasing is, for which x values is my y increasing? Okay? So for instance, over here, this little ant is having to crawl uphill, 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 uphill till we get here. So over here, we are increasing. Okay? So what are the x values for which that occurs? Well, this is going to continue going to negative infinity. And then here, it's going to stop increasing and begin decreasing at negative 3. Okay, from here, this little ant is walking downhill, 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 until we get to this point. So between which two x values is my y value getting smaller? That is negative 3 to a positive 1. Okay, and finally from here on, oh, well, we don't have an arrow there, so we have just a dot, so that means we stop. So from 1 until 4, this function is increasing. Okay, so let's do the same thing down here. What I like to do when I'm doing these functions is I like to kind of diagram my graph. Okay, this right here, I'm getting smaller, 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 smaller until this point. So I like to draw this. Okay, it's getting smaller. Then we're getting larger, 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 larger until here. We're getting smaller, smaller, smaller until here. And then we're going up, 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 up over here. Notice that we change whether we're increasing or decreasing when we have a trough or like a valley or a peak. Every one of those is where something is changing. So let's do our increasing. It looks like to me we're increasing from negative 1 until 0. And we're increasing from 1 to infinity. Do y'all see that? This little piece right here and this piece over here. Ms. Cliven, how do we know that it keeps going? There's not a dot telling us that it stops. Okay, decreasing. Where is this x, like the x values for which y is getting smaller? It's going to continue getting smaller and smaller and smaller and smaller over here. So that's coming from x is negative infinity until a negative 1. And it's also getting smaller in this interval. The x values for which this is getting smaller is 0 to a positive 1. Okay. Over here. Again, here's a peak, so something's happening there. Actually, we're increasing. Here we are decreasing, increasing, decreasing. So we're getting larger, right? These are going to continue going on because they didn't give you dots to stop them. So it's just going to keep going and keep going. So from negative infinity until that looks like negative 1, negative 2. This whole piece is increasing. Then we start decreasing from negative 2 until 0. Then from 0 to 1, we are increasing. And from 1 on, we are decreasing. If you do not use parentheses on these, I will count them wrong. Okay, I want you to try number 3. So pause the video and try number 3, and then come back and see if you're correct. Alright, so here, this one's a little weird because this is happening somewhere in between. Okay, so we're decreasing, increasing, decreasing, increasing. So since you don't know that exact value, it is okay to just say, that looks like maybe negative 1.5. Okay, just make sure that it's somewhere in between those x values. We are increasing from -1.5 until 0. We're decreasing again from 0 until it looks like maybe positive 1.5, and then we're increasing thereon. Okay, so check your work, make sure you did that correctly. Let's keep going. Relative minimum. Okay, relative minimum. A relative minimum is the lowest point on the graph at turns. Okay, relative means around its area. Okay, so just in a particular area of the graph, it's lower than other points. The absolute minimum means that it's the very lowest point. There is no point lower than that point on the graph. Okay. If your graph keeps going on and on and on to negative infinity, you don't have an absolute minimum. Okay. If there are two lowest points, both equally low, they're both the absolute minimum. Example 3 has a really good point there. Right? These are the same amount of being low. So we would say that the minimum is 1.5, -2, and -1.5, -2. Okay. So let's see how that works over here. Approximate the relative minimums and absolute minimums where they exist. So here, let's just think about lowest points, and particularly at turns. Okay, so here's a turn. I've got something going on there. And then here, this point is lower than any of the other points around it. So there's that. Okay, so here, let's just start with this one. This point right here, it is relatively lower than everything else, but notice the definition of absolute minimum. This is the lowest point on the graph, or that will ever be on the graph. So this point right here, -1, is our absolute minimum. This guy over here isn't the very lowest point, but it is lower than other points near it. So this right here would be 4, 1, a relative minimum. Okay, let's try the same thing over here. We have a low point here, and we have a low point here. Is one more low than the others? No, they're about the same. Okay, so we have relative minimums at both, or we don't have relative minimums. Those are both the lowest points on the graph. So we wouldn't have any relative minimums in this graph. We would have an absolute minimum at -1, -1, and at 1, -1. Okay. Relative maximums. Okay. Relative maximum, this is the highest point in a particular area at turns, just like our relative minimum. The absolute means the very highest point. Okay. Again, if our graph continues going on and on and on to positive infinity, then we're not going to have an absolute maximum. And if there are two equally high points, they would both be considered the absolute maximum. So here we go. Relative maximum. I like to go ahead and acknowledge my highest points. So we have a highest point here, and we have a highest point here. Okay. Relative maximum. This right here is higher than any of the points around it, but it's not the very highest point. So this right here would be our relative maximum, the point 2, 0. The very, very highest point, the absolute maximum, would be this point here. So what is that? 2, 4, 6, 8. That looks like 10. -1, 10. Okay. Over here, the relative maximum, let's see. We've got this guy right here. That's our only relative max here. This is a relative max because it's higher than anything right around it, but it's not the highest point on the graph. So that would be the point 0, 4. But as far as an absolute maximum, are we ever going to get to a highest number here? No, those are going to continue going on and on and on to positive infinity, so we do not have an absolute maximum here. At this point, you will do the top portion of the worksheet that you picked up. Please read the instructions. You're doing the top of it today. Next class, we'll do the bottom. If you finish that before the end of class, then you need to continue working on your Texas A&M math placement thing. Don't stress about that. I just want you seeing what college entrance exams are going to look like when they're doing math placement. We're going to start doing those as warm-ups here soon. So finish your worksheet that you picked up today, and then continue working on your A&M math placement exam, please.